How is everyone doing today? I'm just quickly uploading our lecture slides. Did you guys have a great recess? Can everyone still hear me? Okay. How was your guys' recess? So just before recess, we ended off with the sun. And as we know, the sun is our nearest star. So continuing forward, we are now going to look at different kinds of stars. But can any one of you guess why it is important that we started out with the sun first? Yes, it is the easiest to observe. You are correct. And you're also correct. We can use it as a reference. So if we understand the processes that governs our own sun, we can then translate that processes to different stars. And then we can figure out or understand better how those stars work and what governs those stars. So for this lecture, we are going to look at a family of stars, star distances, apparent brightness, intrinsic brightness, and luminosity, stellar spectra, star sizes, star masses, and binary stars. And then we are going to achieve a consensus of what stars are. So just to put this into perspective, in this image right here, right at the end, 1 pixel of this image represents the size of our own sun. And this is different kinds of stars that we can see in our night sky and that we can analyze in our night sky. Our star is an average. Our sun is an average type star, and we will discuss, and at the end of this lecture, formulate a consensus of why it is an average type star and what makes it an average type star. So for this lecture, it is important to answer these questions. So the one is, how far are the stars away? Secondly, how much energy do stars make? Thirdly, how do spectra of stars allow you to determine their temperatures? Fourthly, how big are stars? And then lastly, How much mass do stars contain? So let's try and answer a few of these questions. So how many of these questions can you guys answer immediately? Okay, so Freeman, which three questions can you answer currently? Question number 3, how do spectra of stars allow to determine temperatures? Yes, so we have talked about different spectra, but what we will learn in this lecture is we can determine the temperatures of stars by looking at a spectra. Also, by looking at stars, we can determine how far away they are, but also looking at the temperature in spectra. We can get the same information of how much energy do stars make also from the temperature and spectra. Bigger stars, also temperature and spectra, and how much mass the star contains, we get that also from its temperature and spectra. So those are some important aspects we need to know about stars. So to explain it a little bit better, I'm going to show you a video before we start off with today's lecture.
Little star. Oh, I know who you are. At first glance, stars pretty much all look alike. Twinkly dots scattered across the sky. But as I talked about in episode 2, when you look more closely, you see differences. The most obvious is that some look bright and some faint. As I said then, sometimes that's due to them being at different distances, but it's also true that stars emit different amounts of light too. If you look through binoculars or take pictures of them, you'll see that they're all different colors too. Some appear white, some red, orange, blue, and for a long time, the reason for this was a mystery. In the waning years of the 19th century, astrophotography was becoming an important scientific tool. Being able to hook a camera up to a telescope and take long exposures meant being able to see fainter objects, revealing previously hidden details. It also meant that spectroscopy became a force. Say it with me now. For science! A spectrum is the result when you divide the incoming light from an object into individual colors or wavelengths. This reveals a vast amount of physical data about the object. But in the late 1800s, we were only just starting to figure that out. Interpreting stellar spectra was a tough problem. The spectrum we measure from a star is a combination of two different kinds of spectra. Stars are hot, dense balls of gas, so they give off a continuous spectrum. That is, they emit light at all wavelengths. However, stars also have atmospheres, thinner layers of gas above the denser inner layers. These gases absorb light at specific wavelengths from the light below, depending on the elements in them. The result is that the continuous spectrum of a star has gaps in it, darker bands where different elements absorb different colors. At first, stars were classified by the strengths of their hydrogen lines. The strongest were called A stars, the next strongest B, then C, and so on. But in 1901, a new system was introduced by spectroscopist Annie Jump Cannon, who dropped or merged a few of the old classifications and then rearranged them into one that classified stars by the strengths and appearances of many different absorption lines in their spectra. A few years later, physicist Max Planck solved a thorny problem in physics, showing how objects like stars give off light of different colors based on their temperature. Hotter stars put out more light at the blue end of the spectrum, while cooler ones peaked in the red. Around the same time, Bengali physicist Meghnad Saha solved another tough problem: how atoms give off light at different temperatures. 2 decades later, the brilliant astronomer Cecilia Payne-Gaposchkin put all these pieces together. She showed that the spectra of stars depended on the temperatures and elements in their atmospheres. This unlocked the secrets of the stars, allowing astronomers to understand not just their composition, but also many other physical traits. For example, at the time it was thought that stars had roughly the same composition as the Earth. But Payne-Gaposchkin showed that stars were overwhelmingly composed of hydrogen, with helium as the second most abundant element. The classification scheme proposed by Cannon and decoded by Payne-Gaposchkin is still used today. and arranges stars by their temperature, assigning each a letter. Because they were rearranged from an older system, the letters aren't alphabetical. So the hottest are O-type stars, slightly cooler are B, followed by A, F, G, K, and M. It's a little weird, but many people use the mnemonic, "Oh be a fine guy, kiss me," or "Oh be a fine girl, kiss me," to remember it, which was dreamed up by Annie Jump Cannon herself. Each letter grouping is divided into 10 subgroups, again according to temperature. We've also discovered even cooler stars in the past few decades, and these are assigned the letters L, T, and Y. The Sun has a surface temperature of about 5,500 degrees Celsius and is a G2 star. A slightly hotter star would be a G1, and a slightly cooler star a G3. Sirius, the brightest star in the night sky, is much hotter than the Sun and is classified as an A0. Betelgeuse, which is red and cool, is an M2. Stars come in almost every color of the rainbow. Hot stars are blue, cool stars red. In between, there are orange and even some yellow stars. But there are no green stars. Look as much as you want, and you won't find any. It's because of the way our eyes see color. A star can put out lots of green light, but if it does, it'll also emit red, blue, and orange. And our eyes mix those together to form other colors. A star can actually emit more green light than any other color, but we'll wind up seeing it as white. How do I know? Because if you look at the Sun's spectrum, it actually peaks in the green. Isn't that weird? The Sun puts out more green light than any other color, but our eyes see all the mixed colors together as white. Wait, what? White? You may be thinking the Sun is actually yellow. Not really. The light from the Sun is white, but some of the shorter wavelengths like purple and blue and some green get scattered away by molecules of nitrogen in our air. Those appear to be coming from every direction but the Sun, which is why the sky looks blue. The Sun doesn't emit much purple, so the sky doesn't look purple, and the green doesn't scatter as well as blue. That gives the Sun a yellowish tint to our eyes. And looking at the Sun is painful anyway, so it's hard to accurately gauge what color it appears. That's also why sunsets look orange or red. You're looking through more air on the horizon to see the Sun, so all the bluer light is scattered away. So we can use spectra to determine a lot about a star. But if you combine that with knowing a star's distance, things get amazing. You can measure how bright the star appears to be in your telescope, and by using the distance, you can calculate how much energy it's actually giving off, what astronomers call its luminosity. An intrinsically faint light looks bright if it's nearby, but so does a very luminous light far away. By knowing the distance, you can correct for that and figure out how luminous the objects actually are. This was, no exaggeration, the key to understanding stars. A lot of a star's physical characteristics are related. Its luminosity depends on its size and temperature. If two stars are the same size, but one is hotter, the hotter one will be more luminous. If two stars are the same temperature, but one is bigger, the bigger one will be more luminous. Knowing the temperature and distance means knowing the stars themselves. Still, it's a lot of data. A century ago, spectra were taken of hundreds of thousands of stars. How do you even start looking at all that? The best way to understand a large group of objects is to look for trends. Is there a relationship between color and distance? How about temperature and size? You compare and contrast them in as many ways possible and see what pops up. I'll spare you the work. A century ago, astronomers Einar Hertzsprung and Henry Norris Russell made a graph in which they plotted a star's luminosity versus its temperature. When they did, they got a surprise. A very strong trend. This is called an HR diagram, after Hertzsprung and Russell. It's not an exaggeration to call it the single most important graph in all of astronomy. In this graph, really bright stars are near the top, fainter ones near the bottom. Hot blue stars are on the left, and cool red stars on the right. The groups are pretty obvious. There's that thick line running diagonally down the middle, the clump to the upper right, and the smaller clump to the lower left. This took a long time to fully understand, but now we know this diagram is showing us how stars live their lives. Most stars fall into that thick line, and that's why astronomers call it the main sequence. The term is a little misleading. It's not really a sequence per se, but as usual in astronomy, it's an old term and we got stuck with it. The reason the main sequence is a broad, long line has to do with how stars make energy. Like the Sun, stars generate energy by fusing hydrogen into helium in their cores. A star that fuses hydrogen faster will be hotter because it's making more energy. The rate of fusion depends on the pressure in a star's core. More massive stars can squeeze their cores harder, so they fuse faster and get hotter than low-mass stars. It's pretty much that simple, and that explains the main sequence. Stars spend most of their lives fusing hydrogen into helium, which is why the main sequence has most of the stars on it. Those are the ones merrily going about their starry business of making energy. Massive stars are hotter and more luminous, so they fall on the upper left of the main sequence. Stars with lower mass are cooler and redder, so they fall a little lower to the right, and so on. The sun is there too, more or less in the middle. What about the other groups? Well, the stars on the lower left are hot, blue-white, but very faint. That means they must be small, and we call them white dwarfs. They're the result of a star like the sun eventually running out of hydrogen fuel. We'll get back to them in a future episode. The stars on the upper right are luminous but cool. They must therefore be huge. These are red giants, also part of the dying process of stars like the sun. Above them are red supergiants, massive stars beginning their death stage. You can see some stars that are also that luminous, but at the upper left. Those are blue supergiants. They're more rare, but they too are the end stage for some stars. And again, we'll get to them soon enough in a future episode. But I'll just say here that it doesn't end well for them. But on a brighter note, we literally owe our existence to them. And this implies something very nifty about the HR diagram. Stars can change position on it. Not only that, but massive stars versus low mass stars age differently and go to different parts of the HR diagram as they die. In many ways, the diagram allows us to tell at a glance just what a star is doing with itself. This difference between the way low-mass stars like the sun and higher-mass stars age is actually critical to understanding a lot more about what we see in the sky. So much so that they'll be handled separately in later episodes. I'm sorry to tease so much about what's to come, but this aspect of stars, finally understanding them physically, was a major step in astronomy, leading to understanding so much more. And don't you worry, we'll get to all that. Today you learned that stars can be categorized using their spectra, together with their distance.
Does that give a nice overview of what we are going to discuss? So let's go back to our lecture slides. So here is our lecture slides. So to boldly go where no man has gone before, where does this quote come from? Not Neil Armstrong, it's from a sci-fi series. Where are the Star Trek fans? Yes. Yes, Star Trek. And the first person who said that was James T. Kirk. So, any guesses? Why did I choose to show you guys this quote? Any suggestions? Because space is the final frontier we are yet to conquer. So we've already explored Earth, we've explored the oceans, we've explored the jungles. So next thing is, and the last step is to explore space. So Shakespeare compared love to a star that can be easily and even used for guidance, but whose real nature is utterly unknown. He lived about the same time as Galileo and had no idea what stars actually are. To understand the history of the universe, the origin of Earth, and your place in the cosmos, you need to discover what people in Shakespeare's time did not know, the real matter of the stars. Uninformatively, it is quite difficult to find out what stars is like. So when you look at a star, even through a large telescope, you see only a point of light. Real understanding of stars requires careful analysis of starlight. To find out almost anything about a star, you must know how far away it is. Although knowing distances is crucial, it is also the most difficult measurement in astronomy. Astronomers have found a number of ways to estimate the distances to stars, but each of those ways ultimately depends on a direct geometrical method that is much like the method surveyors use to measure the distance across a river they cannot cross. So one way to do it is by making use of the surveyor's method, and that basically comes down to parallax. So we want to measure what is the distance d across the river. So one thing that we do is you can find the distance d across the river by measuring the length of the baseline and the angles A and B, and then construct a scale drawing of a triangle using geometry to calculate it. So what we do is, with this is, you probably know the land surveyors, or probably see civil engineers on the side of the road, where they have that camera looking thing they look through. Do you know what that camera looking thing is they actually look through? It measures angles. So what we do if you want to measure point C over here, we choose a baseline. So we choose point A and we choose point B. If we choose point A and we choose point B, then we can determine what is the angle of A, what is the angle of B, and then we can just use basic trigonometry to calculate the distance D. Does everybody follow this explanation? Awesome. And we do basically sort of using trigonometry. Yes, basic trigonometry. So remember, in an earlier lecture, we talked about parallax, right? And a parsec. How do you know the angle? Though you can literally measure the angle. You can basically use a protractor, a compass and a protractor, and you can measure the angle. So you guys still remember the distance parallax that we talked about in one of our intro chapters? Can everybody still remember parsec and parallax? So the definition says 1 parsec is 3.2 light years. So how that fits into distance is we can create a distance with parallax from Earth where we can use 1 AU, that's the average distance from Earth to the Sun, as one part of the baseline. So here we can use one part of the baseline. Wait till the Earth is in the other part of the Sun, there's a different part of the baseline, and we look at the distance over there. That means we know this angle over here, this angle over here, and we can literally calculate D. That seems simple, right? So that's one way we can do it. We call this the parallax method. But the problem with the parallax method is the further this star is away, the smaller this angle P becomes. And the smaller that angle becomes, the smaller the parallax we are measuring, and then the more difficult it becomes to find the distance to stars. So therefore we need a better method. So because the stars are so distant, the parallaxes are very small angles. usually expressed in arc seconds. Astronomers conventionally call stellar parallax speed the shift of the stars across 1 AU, so not the 2 AU baseline. So astronomers measure parallax and surveyors measure the angles at the ends of the baseline. But both measurements reveal the same thing, the shape and size of the triangle and this distance to the object in question. The distance to the stars is so large that astronomers have to find a special unit of distance, the parsec, for use in those distance calculations. So question, so the accuracy is about 10% because of blurriness caused by the atmosphere. Yes, that is correct. So that's why when you do these measurements, you try to do as many of these measurements as possible to get the error as small as possible. So as we discussed, the parsec, a parsec is 3.26 light years. So how we measure a parsec is if we are theoretically in a spaceship and we are so far away from Earth that we can see Earth and the Sun, so the baseline is 1 AU, and this angle right here forms 1 arc second, then this distance is 1 parsec, and that is 3.26 light years. So the only thing I will ask you in a test and exam is define a parsec, and you can say a parsec is a measure of distance which equals 3.2 light years. That's just a hint for you guys. Because the stars are so distant, their parallaxes are very small angles, usually expressed in arc seconds. Astronomers conventionally call stellar parallax speed the shift of the star observed across 1 AU, not a 2 AU baseline. Astronomers measure the parallax and surveyors measure the angles at the ends of the baseline. But both measurements reveal the same thing, the shape and the size of the triangle, and thus the distance to the object in question. The distances to stars are so large that astronomers have to find a special unit of distance, the parsec, for use in distance calculations. The visible star nearest to the Sun, Alpha Centauri, in figure 2.5, lists of the famous star as also famous stars. It has a parallax of only 0.747 arc second, and the more distant stars have even smaller parallaxes. To see how small these angles are, hold a piece of paper edgewise at arm's length. The thickness of the paper covers an angle of about 30 arc seconds. So if I ask you a question, for example in a test, let's say one star has an arc second, has this angle of 0.7, and the other one has an angle of 0.2. Which one is closest to Earth? So the one closest to Earth will be the one with the biggest angle. So if you have 0.2 and 0.7, 0.7 has the biggest angle, so that means the one of 0.7 is closer to Earth than the one of 1.2 angle. And this is where we're going to get into parallaxes. So in this example, it's straightforward. It's just to calculate it. So to find the distance to a star from its measured parallax, astronomers use the same calculation you've already seen in the small angle approximation formula. Imagine that you observe our solar system from the star, in figure 8.2 shows the angular separation you would measure between the Sun and Earth equals the star's parallax speed. So recall that a small angle formula relates to an object's angular diameter, its linear diameter, and its distance. In this case, the angular diameter is the parallax angle P, and linear diameter is the baseline of the triangle, which is 1 AU, and a small angle formula rearranged slightly tells you that the distance d to the star in AU equals 2.06 times 10 to the power 5 divided by the parallax in arc seconds. So this is a formula given And I will put that on a formula sheet as well. So here we have distance, here's our constant, and here is our parallax in arc seconds. So the constant 2.06 times 10 to the power 5 is a conversion factor, so the number of arc seconds in a radian. Because the parallaxes of even the nearest stars are less than 1 arc second, the distances in AU is inconveniently large numbers. So to keep the numbers manageable, astronomers have defined the parsec as their primary unit of distance. In that way, that simplifies the arithmetic. 1 parsec equals 2.06 times 10 to the power 5 AU. So then the equation becomes D equals 1 divided 1 parsec. So basically you can use any one of these, but we will use the second form of the equation where we've done the conversion factor. So if we do an example, so the star Altair has a parallax of 0.195 arc seconds. So how far is it away? The solution is the distance in parsecs equals 1 divided 0.195 or 5.31 parsecs. So this is a straightforward plug and play example. Are you guys happy with this? Now you won't have to do unit conversions. I will give everything in the correct units. Awesome. So the blurring caused by Earth's atmosphere smears stars' images and makes a diameter even at a good observatory site, and that makes it difficult to measure parallaxes from Earth. Even when astronomers average together many observations, they cannot measure parallaxes from an observatory on Earth with an uncertainty smaller than about 0.002 arc second. Therefore, if you measure a parallax of 0.02 arc second from Earth, the uncertainty is about 10%. So one way to solve this is by doing the same method with satellites, telescopes, and orbit. So the one was the Hipparcos satellite that was from 1989 to 1993, weighed 500 kilograms, and its sample population, so that means it measured the distance to 100,000 stars with an accuracy of 2 milliarc seconds. The second telescope is Gaia. It operated from 2013 to 2018. It has a mass of 2.03 tons. It's quite heavy. And it measured the position of 1 billion stars and a radial velocity of 150 million stars with a position accuracy of 24 microarc seconds, which is quite amazing. Did you guys realize that these telescopes existed? So those are pretty cool, and both of them was from ESA. Do you know which ESA is? That stands for the European Space Agency. Don't know if you guys realize what that acronym meant as well. So thinking about this, the acronym, so ESA that we have here on the side, that stands for the European Space Agency. It's a pleasure. Do you guys have any questions so far? Okay, so let's continue. So now we're going to start discussing apparent brightness, intrinsic brightness, and luminosity. So if you see a light on dark highway, it is hard to tell how powerful it really is. It could be the brilliant headlight on a distant truck or the dim headlight on a near bicycle. So if we take this analogy, you have a big truck coming with a powerful headlight or a bicycle with a dim light. And depending where you are, the far truck and the nearby bicycle, the brightness will look exactly the same. So to judge the true brightness of a light source, you need to know how far away it is. So the headlight on a distant truck might appear as bright as the light on a nearby bicycle, giving you no clue about their real distance. How bright an object appears depends not only on how much light it emits, but also on its distance from you. A 6 magnitude star, just visible to your eye, looks faint, but its apparent magnitude doesn't tell you how luminous it really is. Now that you know how to find the distance to stars, you can use those distances to figure out the intrinsic brightness of stars. Intrinsic means belonging to the thing. So the intrinsic brightness of a star refers to the total amount of light the star emits. So if I ask you what is the difference of apparent brightness and intrinsic brightness, how would you define it? So question, what causes the light of an object to lose intensity with distance, especially in a vacuum? And then apparent is how much light reaches us. So yes, apparent is, remember we had the apparent magnitude scale. So the apparent brightness is the more smaller number is the brighter. So -1 is more bright than -2. Yes, I see a hand has risen. And then intrinsic brightness is its actual brightness. So question, what causes light of an object to lose intensity? So we can think about it as this sphere over here. So here we have a light bulb in the middle. And then it comes to the example I explained it in an earlier lecture about flux. So when we are a distance of 1 meter away, we have this sheet that is closer to the globe, and more light rays goes through it, meaning it appears brighter. But if you are 2 units now away, then that 1 square unit is now 4 square units. So that means the less light is penetrating through it. And that is what causes it to lose intensity over distance, because light doesn't go in one direction, it spreads out. A good example is if you have a green laser pointer and you point it towards your wall or a whiteboard or something, it appears quite bright because the light is focused onto a single spot. But if you would remove that filter in front of a laser, that it doesn't move in one direction, that it can move in all directions, then it will radiate in all directions, and it will lose intensity the further you are away from it. And we call that the inverse square relation. Does that answer your question? It is a pleasure. And the inverse square relation does not only account for visible light, it accounts for electromagnetic radiation. So the rule is, so let's take an example. How acquainted are you guys with the power of your Wi-Fi signals? Or let me rather restate it. You can actually do an experiment of where you are. So do you guys have actual access to a Wi-Fi router, or can be within 30 centimeters from a Wi-Fi router? Okay, but let's do this as a thought experiment. You can either do this on campus in one of the lecture venues. So you see your lecture venues will probably have a Wi-Fi router or access point mounted on the ceiling, am I correct? Okay, so what is your Wi-Fi strength if you're sitting directly underneath that repeater or access point? Your device will show its full strength, right? Yes, very strong. So it will say, so your cell phone, tablet, computer, or whatever will show full bars on a signal strength, correct? So let's do this thought experiment. I'm going to get a whiteboard. So how it works is it's with light and electromagnetic radiation. The inverse square relation, we write it as 1 over r squared. So now let's take our Wi-Fi example. Let's say we are 1 meter away from our access point. So 1 over 1 squared, that gives us 1, correct? Yeah, this is a horrible R, so let me try and do a little better. So what will be happen to our signal strength if we are 2 meters away? So 1 over 2 squared, what will that give us? 1 over 4. So that means our signal strength or our intensity is now a quarter of what it was. So what will be if we are now 3 meters away? Yes, 1 over 9. And if we are 4 meters away, 1 over 16. So what will happen if we are 10 meters away? 1 over 100. So if we do this, is there a big difference between this value here and that value over there? Yes. And that is exactly how light and all electromagnetic radiation works if it is dispersed equally around in all directions. So when we look at a normal, let's say, sphere, a light source, and we have equal light or radiation emanating in all directions around it. That is how it works, the 1 over r squared law, or the inverse squared law, if you want to call it the English name, but most people call it the 1 over r squared rule. So that is why with your Wi-Fi, the closer you are to your repeat or access point, the stronger signal you have. The stronger signal you have, the more of the bandwidth and more speed you have. The further you are away, the weaker your signal is, the less bandwidth you will have, the less speed you will have. So it tapers off actually quite very fast from 1 meter going to 10 meters. So that is why Wi-Fi struggles to penetrate through different walls as well. And that is why Wi-Fi are moving over to 5 gigahertz, for example, and even now looking at 6 or 7 gigahertz. And that's the same thing for a normal light bulb as well. If you are sitting 1 meter away from a light bulb, you agree that's the intensity is very strong and that's more than enough light to work under. Am I correct? And what will happen to that same light bulb if you're now sitting 10 meters away? Is that enough light to work under? Not enough light. And that's exactly due to this principle, the 1 over r squared principle. So if we now go back to our lecture slides, let's go back to lecture slides. Let me find that slide again. So on this slide, this is exactly how it works. So here is our 1 over r squared relation. So here we are 1 meter or 1 unit or whatever the unit is you are away. So that means if you're 1 away, that's 1 divide 1 square, which is 1. But now if you are 2 meters away, that is 1 over 2 to the power 2, and that equals 1 over 4. So if you're 3 meters away, that is 1 over 9. Does everyone understand where this comes from now? Can you guys still hear me? Awesome. So when you look at a bright light, your eyes respond to the visual wavelength photons falling in your eye's retina. So the apparent brightness you perceive is related to the flux of energy entering your eye. Flux is defined as the energy in joules per second falling on 1 square meter. 1 joule per second is 1 watt, a common unit of energy consumption used, for example, to rate light bulbs. The apparent brightness of a light source is determined by the inverse squared law, like I described right now. So here we can see the relative intensity and the distance we are away. So here we are 1 over 4, 1 over 9, 1 over 16. So here we can see the intensity dropping off quite dramatically. And now this graph puts in perspective how it dramatically changes the further we are away from an object. So now you know why it is difficult to judge the intrinsic brightness of a star. So let's take Alpha Centauri, the closest star we can see with our unaided eye to Earth. That's 4.2 light years away. So we are at 4.2 light years away. This is the brightness. That will be farther. So sorry to disturb you and go off topic, sir. Until what lecture slide should we study for the semester test? So that will be until where we come the week before our semester test. If our planning is correct, that will be up until lecture slide number 10. It's a pleasure. So just to put this into a different perspective, in the middle of day, let's say 12 o'clock afternoon, the sun is right over our heads. The sun is bright during the daylight, so if you will look you don't ever do it, but if you will look to the sun with your unaided eye, it will hurt your eyes, right? And we are 150 million kilometers away from the sun. So keep this inverse square law rule in mind, 1 over r squared. So we are 150 million kilometers away. So we can figure out the relative intensity by saying 1 divide 150 million squared. So what will happen if we move 50 million kilometers closer to the sun? The intensity will increase quite dramatically. So that is why, let's say we are at Mercury, the intensity of the sun is much, much, much greater than what we are used to on Earth. Bit of a side note. Do you guys ever wondered why you cannot look into the sun directly with your unaided eye, or why you cannot shine a laser pointer into someone's eye? The retina will burst and burn, UV rays, but if you ever guys wondered what actually happens to the biology of your eye, why it hurts looking into the sun, why you cannot shine a laser beam into someone's eyes. Or let me rephrase, what is the physical damage it actually causes? So burns retinas. Besides that, what happens when you cook an egg on your stove plate? The yolk, so that means the yellow part becomes quite hard and solidifies. But what happens to the proteins around the yolk? That is the see-through part. That becomes white, right? And that white is the proteins being cooked. So what happens when you look into the direct sunlight or shine lasers into your eyes? So yes, Keegan, you are correct. You damage the photoreceptor due to the heat of being focused. But what damages the physical photoreceptor is you physically cook the proteins in your eye. So that means your eye that is see-through becomes white. The proteins becomes white and solidifies. So that means that puts pressure on the photoreceptor and it blocks light from reaching the photoreceptor that you cannot see. So you literally cook the proteins inside your eye. And that is why you cannot look at the sun. And that is why you cannot shine a laser into someone's eyes, because you literally cook the proteins. I didn't know if you guys realized that. And that is why it is so dangerous. So this is where the 1 over r squared rule comes from, and that is where flux comes from. So you can think about flux as 1 square meter, and here's our source, here is our light rays or electromagnetic rays. So the more of these rays that penetrate through 1 square meter, the higher flux we will have. So now if we are 2r away, so 1 over r squared, this is now 1 over 4, so that means the area is bigger, less rays penetrate through it, the flux will be less. 1 over 3, so 3r squared, so 1 over 9, that means the flux is even more less. Does everyone understand where flux comes in? Awesome. So you can see that if you know both the apparent magnitude of a star, so expressing the flux received on Earth from it, and its distance, you can use the inverse square law to correct for distance and learn the intrinsic brightness of the star. Astronomers do that using a special kind of magnitude scale described in the next section. So now we're going to look at a absolute visual magnitude. If all stars were the same distance from Earth, you could compare one with another and easily determine which one was emitting more light and which less. Of course, the stars are scattered at different distances, and you can't shove them around to line them up for comparison. If, however, you know the distance to a star, you can use the inverse square relation to calculate the brightness the star would have at some standard distance. Astronomers has adopted the 10 parsec as the standard distance and referred to the absolute visual magnitude of a star as the apparent visual magnitude it would have if it were 10 parsecs away. Is everyone following? Okay. So to find a star's absolute visual magnitude, you begin by measuring its apparent visual magnitude. So in other words, its brightness. A relatively easy task. Then you need the distance to the star. If the star is nearby, you can measure its parallax and from that calculate the distance. Once you know the distance, you can use a simpler formula to correct the apparent visual magnitudes for its distance and find the absolute visual magnitude. So here is a formula of how we are going to do it. So apparent visual magnitude tells you how bright a star looks. So see reasoning with numbers 2.1, we have looked at this. But absolute visual magnitude tells you how luminous the star really is. The absolute visual magnitude of the star is the apparent visual magnitude a star would have if it were 10 parsecs away. If you know a star's apparent visual magnitude and its distance, you can calculate the absolute visual magnitude, the magnitude distance formula that shows this calculation relates apparent visual magnitude MV, distance in parsecs, so D, and absolute visual magnitudes MV. So here we have MV. So our small MV is our apparent visual magnitude. The big MV, that is our absolute visual magnitude, minus 5 plus 5 log phi log D, and D is the distance in parsecs. So the expression log means logarithm to base 10. So sometimes it is convenient to rearrange the equation and write it as D equals 10 times D. What is a little mv? That is our apparent visual magnitude. Big M is our absolute visual magnitude, plus 5, close the bracket, to the power 5. So it's the same equation you can write, you can use whichever form is most convenient in a given problem. So if you know the distance, the first form of the equation is convenient. But if you're trying to find the distance, the second form from the equation is best. So in this example, the famous star Polaris is 133 parsecs from Earth, and it has an apparent magnitude of plus 2. So what is the absolute visual magnitude? So the solution, you can do it in a pocket calculator. You plug in the equations. We solve for big capital MV, which is the absolute visual magnitude. And then we can calculate it as minus 3.6 if it were 10 parsecs away from Earth. Are you guys happy with this explanation? Awesome. So how does the sun stack up against other stars? The sun is tremendously bright in the sky, but it is also very nearby. Its absolute visual magnitude is just 14.8. If the sun were only 10 parsecs from Earth, about 33 light years, not a great distance in astronomy, it would look no brighter than the faintest star in the handle of the Little Dipper. So here we can put it in perspective. If the sun were 10 parsecs away, it will look like this faint star over here. So the intrinsic brightness stars known have absolute visual magnitudes of about 28.3, which means that such a star 10 parsecs from Earth will be more than 25 times as bright as Venus at its brightest. Such stars have intrinsic brightnesses of 13 magnitudes brighter than the sun, which means they are emitting over 100,000 times more light than the sun. In contrast, the intrinsically fainter stars have absolute visual magnitudes of plus 16 or fainter. They are 11 magnitudes fainter than the sun, meaning they are emitting 25,000 times less light at visible wavelengths than the sun. So the next important thing we need to talk about is luminosity. The luminosity L of a star is the total energy that star radiates in 1 second. Hot stars emit a great deal of ultraviolet light that you can't see, and cool stars emit mostly infrared light. Absolute visual magnitude includes only visible radiation. So astronomers must make a correction, sometimes quite large, to account for the invisible energy. Then they can calculate the total luminosity of the star from its absolute magnitude. So astronomers often express luminosities in solar units, meaning they write 2.5 and the L and its little round circle with a dot. So when we have here this little round circle with a dot next to a symbol, that means the solar something. So if we have L and this dot afterwards, that means the solar luminosity, and that means our own sun. For example, if we have a big M and the same symbol afterwards, that means the solar mass, and the solar mass is the mass of our own sun. Do you understand the solar unit of solar luminosity, solar mass, or solar whatever? So let me write it out. If we have this symbol next to a letter, that means solar. So if we have L and this symbol next to it, it means solar luminosity. So that means the luminosity of our own sun. If we have a M and the symbol afterwards, that means solar mass, which means the mass of our own sun. So you guys happy with that terminology? Okay, so in this explanation, if we write 2.5 L in the symbol, so 2.5 solar luminosity, it represents a star that is 2.5 times brighter than our own sun, because our sun is one solar luminosity. If it is 2.5 times the M in a solar unit, it means 2.5 times our sun's mass. Are you guys happy with this explanation? Awesome. So to find the luminosity of a star in joules per second, you can simply multiply the luminosity of the sun in those units times 3.8 times 10 to the power 26 joules per second. So famous star Aldebaran has a luminosity of about 425 solar luminosity, which means it corresponds to 6.5 times 10 to the power 28 joules per second. The most luminous stars emit at least 1 billion times more energy per second than the least luminous. So clearly the family of stars contains some interesting characteristics. Observations of spectral lines give you information about what types of atoms are in the atmospheres of the sun, planets, and stars. So a question, how do we determine what is the composition of an exoplanet? So that means a planet not part of our own solar system. So that means of a planet orbiting a different star. How do we determine its atmospheric composition? Any ideas? Any suggestions? You are basically correct. So what we do is, let me clear this. If this is the star we are observing, and this is a planet orbiting around a star, we wait for it continues in its orbit, and we wait for that star of that planet to pass in front of that star. We call it transit that star. Then from that star, its light will move through that planet's atmosphere. then the light going through that planet atmosphere creates a continuous spectrum. And that in that continuous spectrum, we can see emission and absorption lines. And then from that, we can see what elements are in that atmosphere. And then we know what the atmospheric composition of that planet is. And we can also determine what percentage of its composition is. So how much of a certain molecule or element is in that planet's atmosphere. And then we will get something like this. And in this, we can see it has, for example, hydrogen, helium, oxygen, or whatever. So you guys understand how we determine the composition of a different planet's atmosphere? Awesome. In the late 1800s and early 1900s, when astronomers were making the first careful studies of stellar spectra, the big differences observed between spectra of different stars were thought to show that stars have a wide range of compositions. In the 1920s, Cecilia Payne made use of information from atomic physics and the new field of quantum mechanics to reinterpret the spectra of stars. Payne's calculations showed that over 90% of the atoms in the Sun and other stars must be hydrogen, and most or the rest are helium. Payne discovered that 1, the chemical composition of the Sun is like the composition of other stars. 2, the spectra actually provide information mostly about the temperatures of stars. And thirdly, stars with similar spectra must have similar temperatures. And this brings us to the Balmer thermometer. So one of the main methods Payne first developed for using spectra to determine stars' temperatures is now called the Balmer thermometer. So recall that astronomers use the Kelvin temperature scale when referring to stellar temperatures. Can you guys remember why we use the Kelvin temperature scale? Yes, it is linear, it's constant. So if we speak about SI units for temperature, the SI unit for temperature is Kelvin. And it's because it is linear. So linear, you can see, say, 4 degrees Kelvin is twice as warm as 2 degrees Kelvin. That we cannot do the same thing with Celsius and Fahrenheit. So the Celsius temperature scale refers to water at what Celsius temperature does water freeze, which is 0 Celsius, and at which Celsius level does water evaporate. That's 100 degrees Celsius. Fahrenheit is based on the human feel. So if you would ask a human how hot it feels outside, if it is a hot summer's day in Fahrenheit, that will be between 90 and 110 Fahrenheit. A quite coolish day is 60 Fahrenheit, but again, those two scales are not linear. So you cannot say 20 degrees Celsius is twice as warm as 10 degrees Celsius, or 20 degrees Fahrenheit is twice as warm as 10 degrees Fahrenheit. It doesn't work that way because those scales are exponential, but to make it easier to understand, we use Kelvin, which is a linear scale. Everybody following that explanation? Awesome. So these temperatures range from about 2,300 Kelvin to 50,000 Kelvin. So compare these extremes with the surface temperature of the Sun, which is about 5,800 Kelvin. From information about blackbody radiation and Wien's law, you already know how to estimate a star's temperature by using its color. But the spectral lines of hydrogen at wavelengths visible to the human eye, called the Balmer lines, combined with fewer other spectral lines, give you much greater precision in estimating stellar temperatures. The Balmer thermometer works because the strength of the Balmer lines depends on the temperature of the star's surface layers. So both hot and cool stars have weak Balmer lines, but medium temperature stars have strong Balmer lines. That is because the Balmer absorption lines are produced only by atoms with electrons in the second energy level. So here we can look at hydrogen. So here we can see the hydrogen Balmer lines are strongest for medium temperature stars with photospheres of about 10,000 Kelvin. So here we can see it's weak at 50,000. And here we can say it's weak at around 5,500, but it peaks at 10,000 Kelvin. So lines of ionized calcium are strongest at lower temperatures than the hydrogen Balmer line. So here we can see ionized calcium is at 4,700 degrees Kelvin. And here we can look at other atoms as well. So the spectral lines of each atom, ion, or molecule are strongest at a particular temperature. During the 1890s, astronomers at Harvard Observatory invented the first widely used systems for classifying stellar spectra. One of those scientists, Annie J. Cannon, personally inspected spectra of over 250,000 stars. Spectra were classified into groups labeled A through Q, but some of these groups were later dropped, merged with others, or reordered. So the final classification scheme includes 7 major temperature spectral classes, or types still used today: O, B, A, F, G, K, and M. So a good way to memorize these lines is by using O for O, be a fine girl, kiss me, or O, be a fine guy, kiss me. So that's just a good rhyme to remember it, with O being the hottest and M being the coldest. You guys happy with this explanation? You remember that little rhyme? So in a test or exam, I can give you a list of stars and I can ask you which one is the hottest, which one is the coldest. And then from this classification, you should know, if I give you, for examples, the stars B, A, and F, which one will be the hottest? B, and the coldest will be F. And that's the type of question I can ask you. So during the sequence of spectral types called the spectral sequence is a temperature sequence. The O stars are the hottest, and the temperature decreases along the sequence to M stars, the coolest. For better definition, astronomers divide each spectral class into 10 subclasses. For example, spectral class A consists of subclasses A0 to A9. Next come F to F9, and so on. So this finer division gives stars temperature to precision of about 5%. So the Sun, for example, is not a G star, but a G2 type star. So in this explanation, we can say a 0 star is hotter than a 1 star, and a 1 star is hotter than an A2 star. You guys understand this definition? Awesome. So one thing, so who of you are Star Trek fans? Any Star Trek fans in the class? So in Star Trek, that's something that is scientifically accurate. If they say they are now in an orbit around a G2 type star, you know where that comes from. That comes from this classification. That is one thing the writers of Star Trek got right. So if you're watching Star Trek and they are around a planet with a Earth-like sun, they will always call it in a show a G2 type star. So that's just something interesting on the side. So here we can see spectral class is an O. Its temperature is about 40,000 Kelvin. It is weak Böhme-Line. Other spectral lines features is ionized helium, and the naked eye example is Uranus. So we can see an N-type star is 3,000 Kelvin, and that gives us a good reference to how the different class stars work and compare. Color photographs of stellar spectra ranging from O hot stars at the top to cool M stars at the bottom. So here we can see the hydrogen Böhme lines are strongest at type A0, but the two closely spaced lines of sodium in the yellow are strongest for very cool stars. Helium lines appear only in the spectra of hottest stars. Notice that the helium lines visible at the top spectra has nearly but not exactly the same wavelength as the sodium lines visible in cooler stars. So bands produced by the molecules titanium oxide are strongest in spectra of the cooler stars. So here we can see how these different classifications spectra differs from one another as well. So here we can see spectra often represented as graphs of intensity versus wavelength, with dark absorption lines appearing as sharp dips in the curves. So this set of spectra displays hot stars at the top and cool stars at the bottom. So Böhme lines are strongest at spectral type A0, where lines of ionized calcium are strongest in K stars. Titanium oxide bands are strongest in M stars, and compare these spectra of the information in figures 8.4c and 8.5. Now you can learn something new about some of our famous stars. So Sirius, brilliant in winter sky. So Sirius is also the brightest sky we can see with the unaided eye. Currently around now where the sun sets is the brightest sky you can see is an A1 star. And Vega, bright overhead in the summer sky, is an A0 star. So they have nearly the same temperature and color, and both have strong Böhme lines in their spectra. So the bright and red star in Orion is Betelgeuse, is a cool M2 star. But blue-white Rigel is a hot B8 star. Polaris, the North Star, is an F8 star and a bit hotter than our own sun. In Alpha Centauri, the closest star to the sun, is a G2 type star, just like our own sun. So now the study of spectral types is more than a century old, but astronomers continue to discover and define new types of stars. The L dwarfs found in 1998 are cooler and fainter than M stars. They are understood to be objects smaller than stars but larger than planets and are called brown dwarfs, which you will learn more about in later chapters. So the spectra of M stars contain bands produced by metal oxides, such as titanium oxide. But L dwarf spectral contains bands produced by molecules such as iron hydride. So the T dwarfs are even cooler and fainter type of brown dwarf than L dwarfs. So the spectra shows absorption by methane and water vapor. In 2011, astronomers using infrared space telescopes, large ground-based telescopes, and highly sensitive infrared detectors discovered a class of objects with temperatures below 500 Kelvin that is labeled white dwarfs. And to explain this better, a video on brown dwarf. So let me just quickly get that video and show it to you guys. That will explain it a little bit better.
We now know is full of stars. And planets. Stars are massive enough to fuse hydrogen into helium in their cores, generating energy. The heat created by that process tries to expand them, but their gravity balances that outward force, creating an equilibrium. Planets, even gas giants like Jupiter, are far too small to generate fusion. The stuff inside them resists being squeezed, so their gravity is balanced by simple gas pressure. Jupiter is only about 1% the mass needed to have fusion going on in its core. That's a pretty big gap between a big planet and a small star. It's natural to ask, what would happen if we dumped more mass onto Jupiter? Eventually, it would become a star. The pressure in its core would get high enough to initiate hydrogen fusion. But what if we stopped just short of that? What if we have an object far more massive than a planet, but not quite massive enough to become a true star? What sort of thing would we have then? What indeed? By the late 1950s, astronomers were starting to get a pretty good handle on how stars worked. The mathematical equations that govern the physical processes of fusing hydrogen into helium were being worked out and applied to what we knew from observing the stars themselves. In the 1960s, the idea that you could have a star with a minimum mass was becoming clear. If it had less than about 0.075 times the sun's mass, roughly 75 times the mass of Jupiter, it simply lacked the oomph needed to squeeze hydrogen together hard enough to generate fusion. What would such an object look like? Well, it might form like a star, collapsing from a gas cloud just like the sun did 4.6 billion years ago. But instead of turning on and becoming a star, it would simply sit there, cooling. It might start off pretty hot due to the physical forces that made it, but it couldn't sustain that heat. Like a charcoal ember, it would radiate its heat away. After a few billion years, it would be cold, black, and for all intents and purposes, dead. As people started working out what such an object would be like, they tried to come up with a name for them. These things were black and small, but the name black dwarf was already being used for another type of object. Some people called them substellar objects, but that wasn't terribly catchy. Really low-mass stars are red, and these new objects would be so cool that they'd emit light in the infrared and almost nothing at all in the visible. So they're somewhere between red and black. Jill Tarter, then a young astronomer working in the field, but who later made a name for herself looking for aliens, and oh boy, we'll get to that later, dubbed them brown dwarfs. She didn't mean it literally. Stars can't be brown, but the name stuck. Work proceeded in figuring out what brown dwarfs were like, and a lot of progress was made despite there not being any actual examples of them found. But the hunt was on. Now, as I talked about in episode 26, astronomers classify stars by their temperature. The hottest are O stars, then B stars, which are slightly cooler, down through A, F, G, K, and with the coolest stars being M. But then in 1988, astronomers found a star that was so cool it was distinct from even the M-class stars. It was the first of a new cooler class of stars, so it was given the letter L. Why L? Because there wasn't any other astronomical object that used that letter, so why not? Many more such L stars were found, but still, these weren't true brown dwarfs. These stars were massive enough to initiate fusion in their cores. Worse yet, when brown dwarfs are first born, they're very hot. They can mimic higher mass L stars for a while, looking just like them, making it hard to distinguish between the two. But then a way out was found. A low-mass brown dwarf, it was determined, would have lithium in it, whereas normal stars wouldn't. Lithium is an element, the next one in the periodic table after hydrogen and helium. It can be fused much like hydrogen can, and regular stars would quickly use up their supply of lithium when they were still young. Brown dwarfs, lighter than about 65 times the mass of Jupiter, wouldn't fuse lithium at all. Very careful observations of an object would be able to detect lithium if it were there. That would provide a test to distinguish brown dwarfs from regular stars. The lithium test isn't perfect, but it does work under a lot of circumstances. Astronomers began using it to look for actual, real brown dwarfs. And so they found one. In 1995, a group of astronomers was observing the Pleiades, a nearby cluster of stars that's visible to the naked eye. They were trying to find the faintest stars they could in the cluster to get a complete sample of its membership. The advantage of this is that the distance to the cluster was pretty well known, so a faint star in it must be very low mass. They found an oddball object, which they named Theta 1. It was very red and cool, and best of all, lithium was found in its spectrum. The best models of stellar mass showed that it had about 50 times the mass of Jupiter, or 0.05 times the mass of the Sun. It was clearly substellar. Huzzah! The very first true brown dwarf had been found. At just about the same time, astronomers found that another nearby star, called Gliese 229, had an extremely faint companion. Spectra showed that it was even weirder than Theta 1. It also had lithium, and so was clearly a brown dwarf, but its spectrum showed it had methane in its atmosphere. Methane is a delicate molecule and would break down even in the mild heat of Theta 1's atmosphere. This new object, called Gliese 229b, was even cooler than Theta 1. It was looking like we needed yet another letter to classify stars, and so T-dwarfs became a thing. On a personal note, when I worked on Hubble Space Telescope, Gliese 229b was one of our camera's first targets after it was installed on Hubble in 1997. I was lucky enough to work on the spectrum we took of it, and it was freaky. It emitted almost no light in the visible part of the spectrum and rocketed up in the infrared. I'd seen a lot of stellar spectra before, but nothing like this. Remember, Gliese 229b had only been discovered 2 years before. I became so intrigued by it, I wound up studying low-mass stars and brown dwarfs for several years after. Well, it didn't take long before more brown dwarfs were found. In 2009, NASA launched the Wide Field Infrared Survey Explorer, or WISE, an orbiting observatory designed to scan the entire sky looking at infrared light. It found hundreds of brown dwarfs, and now at least 2,000 are known, with more found all the time. Some are so cool that they form yet another classification, Y dwarfs. So now we have O, B, A, F, G, K, M, L, T, and Y. You're on your own for an acronym here. So if brown dwarfs aren't brown, what color are they? Some are so cool they don't emit visible light at all, so they'd be black. You could be right over one and you wouldn't see it. But some are still warm and so give off some visible light, feeble as it might be. What color would they look? Funny thing, they might be magenta. You'd think they'd be really red because of their temperature, but it's a bit more complicated than that. Remember, they have molecules in their atmospheres that absorb specific colors of light. In some brown dwarfs, there are molecules like methane and even water, well, steam at those temperatures, that are pretty picky about what colors they absorb. Some of these molecules block more red light than blue, so that messes with their colors, making them look magenta. WISE takes pictures in the infrared, which our eyes can't see. To make pictures, astronomers map each infrared color to one our eyes can see. So an image using the shortest wavelength infrared detector is displayed as blue, the medium wavelength one green, and the longest one red. Brown dwarfs put out a lot of light in the intermediate wavelength WISE sees, so weirdly, they appear green in WISE pictures. That does make them easy to spot in those images, even when thousands of other stars are visible too. The physical nature of brown dwarfs is just as weird as you'd expect. For one thing, they have a very unusual characteristic. As they get more massive, they don't get any bigger. Usually, if you dump mass onto an object, it gets bigger. Take 2 lumps of clay and smush them together, and you get one more massive, slightly larger lump. Same with planets and stars. But brown dwarfs are different. At their cores, the density is very high, and the physics is a bit different than what you'd expect. The details are complex, but the end result is that when you add more mass to them, they actually get denser, not bigger. This effect becomes important right around the mass of Jupiter, which means that a brown dwarf, twice as massive as our biggest planet, won't actually be a whole lot bigger. So what's the difference between a small brown dwarf and a really big planet? Well, not much. Nature isn't as picky as we are about having narrowly defined borders between classes of objects. Some people say a planet forms from a disk of material around a star, growing larger as it accretes stuff, while a brown dwarf collapses directly from a cloud of gas and dust. But then you could have 2 objects the same mass and which look exactly the same, yet one would be a planet and one a brown dwarf, depending on how they formed. That strikes me as inconvenient. Astronomers are still debating this, and it gets worse. For example, as I said before, brown dwarfs over 65 times Jupiter's mass fuse lithium. It turns out that ones more massive than about 13 times Jupiter can also fuse deuterium, an atom that's very similar to hydrogen, except it has a proton and a neutron in its nucleus. But neither of these fuses actual hydrogen, so they're not considered true stars. That's still a little arbitrary, so again, I don't make too much of a fuss about it. I think it's best not to think of them as planets or stars, but something with characteristics of both. For example, the way their atmospheres behave depends a lot on how hot they are. In some, iron is vaporized, a gas. In others, they're just cool enough that iron condenses out of the atmosphere, which means it literally rains molten iron. One more thing. The nearest star to the sun is a red dwarf called Proxima Centauri, which orbits the binary star Alpha Centauri. It's about 4.2 light years away. In 2013, astronomers announced the discovery of a binary pair of brown dwarfs called Luhmann 16. They're only 6.5 light years away and became the 3rd closest known star system to Earth. You gotta wonder, could there be an even fainter, cooler brown dwarf closer to us? We know there's none in our solar system, even out in the Oort cloud. It would have been seen by now by one of several different sky surveys. But a light year or 2 out? Maybe. Is Proxima Centauri really the closest star, or will we find one even closer? It seems unlikely, but no more unlikely than the existence of brown dwarfs themselves. Maybe sometime soon we'll have to rewrite astronomy textbooks again. Today you learned that brown dwarfs are objects
So that gives you guys an overview on dwarf stars. We will talk about them in a later chapter in more detail. So let me get a lecture slide again. So from this, we know now that white dwarfs has a temperature of about 500 Kelvin. So these 6 infrared spectra show the differences between L dwarfs and T dwarfs to spectra of M stars. So in the bottom, we can show thick titanium oxide bands, but L and T dwarfs are so cool that other molecules such as iron hydride dominate their spectra. So now we can get to star sizes. Now that you know the luminosities of stars, you are ready to find their sizes, usually expressed as radii or diameters. So recall that astronomers can't see stars as disks through astronomical telescopes. The diameters of a few stars have been measured, and the surface features on a very small number of stars, including the famous star Betelgeuse, have been distinguished using the technique of interferometry. But essentially all stars look like point of light, no matter how big the telescope. Nevertheless, there is a straightforward way to find the sizes of stars. If you know a star's temperature and luminosity, you can determine its radius. The relationship will introduce you to the most important diagram in astronomy, which sorts stars by temperature, luminosity, and size. And in later chapters, you will learn about the life cycle of these stars. So here we can put the sizes of stars into perspective. Here, our own sun is the size of 1 pixel on this image. Did you guys actually know our own sun has a name? It's called Sol, S-O-L. And you guys know where that comes from? Yes, you are correct. It's sun in Greek. So in some places, what is our solar system is called the Sol system. So when we want to know the sizes of stars, we need to know its luminosity, radius, and temperature. So to use the luminosity and temperature of a star to find its size, you first need to understand the 2 factors that affects a star's luminosity: surface area and temperature. You can eat dinner by candlelight because a candle flame has a small surface area. Although the flame is very hot, it cannot radiate much heat. It has a low luminosity. However, if a candle flame is 12 feet tall, it would have a very large surface area from which to radiate, and although it might be no hotter than a normal candle flame, its luminosity would drive you from the table. So that means it all depends on the surface area. So in this image, we can see molten lava pouring from a volcano is not as hot as a candle flame, but the lava flow has more surface area and radiates more energy than a candle flame. So approaching a lava flow without protective gear is therefore dangerous. In a similar way, a hot star may not be very luminous if it has a small surface area, but it could be highly luminous if it were larger and had a large surface area from which to radiate. On the other hand, even a cool star could be luminous if it had a large surface area. Because of this dependence of both temperature and surface area, you need to separate their effects to find the sizes of stars. The Hertzsprung-Russell, or in short the HR diagram, named after its originators, the Netherlands astronomer N.J. Hertzsprung and the US astronomer Henry Norris Russell, is a graph that separates the effects of temperature and surface area on stellar luminosities and enables astronomers to sort and classify stars according to their sizes. So an example, if we would, for example, take cars, you could normally analyze automobiles or cars by plotting their horsepower versus their weight, and this reveal relationships between various models. Most would lie somewhere along the main sequence of normal cars. So here, if we can plot horsepower versus weight, we can plot economy cars, normal cars, racing cars, sports cars. But we can do the same thing with stars. So in an HR diagram, the location of a point tells you a great deal about the star it represents. Points near the top of the diagram represents very luminous stars, and points near the bottom represent very low luminosity stars. Points near the right edge of the diagram represents very cool stars, and the points near the left edge of the diagram represents very hot stars. So here we can see the temperature. So if we move right on the x-axis, it becomes cooler. If we move left on the x-axis, it becomes warmer. If we move up in a y-axis, the luminosity is greater. If we move lower in a y-axis, the luminosity is lower. And then here is the central line. We will come to the central line and explain it, but here we can see as Earth. So here we can see fainter stars are plotted as points near the bottom. Hotter stars are blue and light to the left. More luminous stars are plotted towards the top of the HR diagram, and cooler stars are red and light to the right. Does this make sense to everyone? Awesome. The main sequence is the region of the HR diagram running from upper left to lower right, and it includes roughly 80% of all stars. As you might expect, the hot main sequence stars are more luminous than the cool main sequence stars. So notice in the HR diagram that some cool stars lay above the main sequence. Although they are cool, they are luminous. And that must mean they are larger and have more surface area than main sequence stars of the same temperature. These are called giant stars, and they are roughly 10 to 100 times larger than the Sun. So there are supergiant stars at the top of the HR diagram that are over 1,000 times the Sun's diameter. At the bottom of the HR diagram lie the economy models. Stars that are very low in luminosity because they are very small. At the bottom of their main sequence, the red dwarfs are not only small, they are also cool. And that gives them low luminosities. In contrast, the white dwarfs lay in the lower left of the HR diagram and are low in luminosity that you would expect given their high temperatures. That must mean they are very small. Although some white dwarfs are among the hottest stars known, they are so small they have very little surface area from which to radiate, and that limits them to low luminosities. So here we can see a relationship between luminosity, radius, and temperature in this example. So the luminosity L of a star depends on two things, its size and its temperature. If the star has a large surface area from which to radiate, it can have a high luminosity. So recall the discussion of blackbody radiation in reasoning of number 6.1. The amount of energy emitted per second from each square meter of the star's surface is omega times t to the power 4. Thus, the star's luminosity can be written as the surface area in square meters times the amount it radiates from each square meter. So L equals surface area times omega t to the power 4. Because the star is a sphere, you can use the formula surface as 4 pi r squared, then replace it in the equation, which becomes in this form over here. So this may seem complicated, but if you express luminosity, radius, and temperature in proportion to the Sun, you get a simpler form. So L is the one we want to calculate of a different star, and L with the symbol is our solar luminosity, a solar radius, solar temperature. So in example A, suppose a star has 10 times the Sun radius, but only half the temperature. How luminous is it? So then you plug everything into this equation and you can find it's 6.25. So the star therefore has 6.25 times the sun luminosity. And you can also use the formula to find sizes of stars. So in this example, suppose you measure the apparent brightness and parallax of a star and thereby determine its intrinsic brightness. The star spectrum shows it has a surface that is 2 times hotter than the sun's. That allows you to correct the intrinsic brightness to include non-visible radiation. You calculate that its total luminosity is 40 solar luminosities. What is the radius of the star relative to the sun's radius? So noting the star's luminosity and temperature, you can find its radius and you plug in everything. And then you can calculate the star is 60% larger in radius than the sun. So these are straightforward plug and play equations. So ladies and gentlemen, I think this is what we're going to call it for today. Our lecture ends 5:15. So I'll remain active for another minute or two. Otherwise, have a great day and I'll see you all in class on Monday. Have a great day, everyone. So do we get marks based on attendance? Because according to the ClickUp, I've only attended. No, you're not getting marks according to lectures. I only use it for attendance. So you write a Word template for some. Yes, thank you for reminding me. I will upload it in the next hour. It's a pleasure. It seems like there are no further questions, so I'm also going to log off. Have a great week, everyone, and see you all in next Monday's class.